Yeah, you can start.
Okay, so let's continue our discussion. Last time we had talked, the last two lectures we talked about these sort of randomized complexity classes like RP, co-RP. Then we defined this notion of sampler, and we talked about two types of sampling. One is the independent sampler, and the other was the pairwise sampler, in which the a sampler was basically trying to pick some T random sets of random coins, but in the independent case, these T random coins were picked in a purely independent fashion, fully independent fashion. In the pairwise independent, they were picked in a pairwise independent fashion. We will see all of this. We will try to abstract this a little more and see if we can get better samplers, and that will lead us to the notion of graph expanders, which will be the main focus of our investigation for the next 5 lectures or so. So let's get started. So recap from last time, we had this, we talked about this class BPP, which is sort of the randomized complexity class. And what now, given when we talk about a complexity class like this, like BPP or RP or co-RP, or even P, which is this one, the way we defined it was a collection of problems. It was a collection of languages, decision problems, 0-1 problems, which have some properties. Now, it's hard to actually work with this whole collection. It will actually be useful to work with a specific problem, which is sort of the prototype problem in this class, and sort of just see how that can we design better algorithms for that class and show that if this algorithm is easy, then the whole class is easy. So suppose you want to ask, does problems in BPP, the definition says it requires randomness, but do they actually require randomness? And you want to show that BPP is actually equal to P. One way of doing it, the definitional way of doing it is to show every problem in BPP is actually, you can eliminate the randomness. This is sort of, you don't want to do it problem by problem. So if you had sort of a prototype problem for BPP, if you manage to show that problem doesn't have randomness, if you can manage to show that problem is sort of characterizes the entire class, then it will be nice to work with such a class. So what we will be doing in the first 10 minutes or so, we'll try to understand a prototype problem for BPP. This in the complexity jargon is called a complete problem. I will not define this. I will not define the notion of completeness, but you'll see what it means. It will sort of, by the time we look at this prototype problem, we will see what the notion of why it is the typical problem in BPP. For technical reasons, BPP does not have a complete problem. We actually can't work with languages. We'll have to work with something called promise problems. So, and this will be useful for us anyway. So let me go ahead and define this notion. So what's a promise problem? It's sort of a generalization of what we called of decision problems or languages, what we have so far referred to as languages. And what is it? So whenever you're talking about a language or a decision problem, there was an underlying alphabet. Let sigma be the underlying alphabet. So it must have at least 2 symbols. So typically, we will usually be always working with the alphabet being the Boolean alphabet. But all of this works for any finite. It's a constant sized alphabet. And what was a language? A language, the way we defined a language was just some subset of this sigma star. We took sigma star and some subset of it was a language. These were what we wanted the algorithm to say yes on, and on everything else we wanted to say no on. Now a promise problem is going to be a slight different definition for it. So we'll say pi is a promise problem. If pi pi will actually have two parts to it, pi y, pi s, and pi no, such that the following is true. Pi y, pi no, both are subsets of sigma star, both are collection of strings, they are disjoint. That's all I want of these two. So notice this is almost like a language, and a language, pi y was L, pi y was the S instances, and everything else was the no instance. But what we have in a promise problem is there are some extra, there are what we call, there is sigma star minus pi y union pi n. These are some instances which I don't care. These are what I'm going to call don't care instances. I really don't. These are instances for which I only care how the algorithm behaves on pi y and pi no. I don't care what the algorithm does on the don't care instances. The algorithm could loop, it could go on an infinite this one, it could halt, it could give a wrong answer. There is no answer. I'm not defining the problem at all for this. Notice that we always work with promise problems. That is, when I ask, suppose in the case of primes, you're saying some inputs, you want given a number, you want to check if the number is prime or composite. No, the input need not be a number itself. It could be a graph. And then obviously the algorithm is going to output on this. The input could be gibberish. The algorithm is going to say reject on this. But all of these cases, so we never actually made this point precise previously, because these don't care instances, the algorithm could determine what is a don't care instance. You could look at the input and say, oh, this is an input I don't care for, so I will reject. So you could, but there might be cases in which the algorithm might not be able to look at the input and realize it's a don't care instance. So, but yet we don't care what the algorithm behaves on this instance. So the difference between, if you pictorially, if you want to put it, if you look at, this was sigma star, and a language was just a subset L, and everything else was L complement. That was what a language or a decision problem was. In the case of this one, there is a S instance where you're going to care, you want the algorithm to output accept. There's a no set of no instances, and then there's a set of don't care instances. And what I wanted to impress is we always have been working with promise problems. It's just that in the typical case, the don't care instances, it's easy to realize what's a don't care instance. Sometimes it might not be, but the point is I really don't care. I don't care what the algorithm does. All I want to know, it has to distinguish yes guys from no guys. It has to distinguish primes from composites. You give it a car in between, I don't care what the algorithm is going to do to this input. So when you give it an S input or a no input, a car actually is not a feasible input. It's not a member of the sigma star, but you give something else. As long as you give it something which has no meaning, I don't care about it. You only care, so you care about the S, the no. So there's nothing non-trivial going on, but it will be easier for us to work with promise problems rather than languages. Is the second clear? And we have always been working with promise problems. So let's just define promise BPP. So promise BPP. So we'll put a promise. This is spelled promise BPP is the set of promise problems pi 1 such that there exists a polynomial time randomized algorithm A satisfying. It's the exact same definition as we said before when we say if X is in pi Y, then the probability over the random coin tosses that A of XR accepts should be greater than or equal to 2/3. If X is in pi no, then probability that A of XR accepts should be less than or equal to 1/3. And I don't care about its behavior elsewhere. Of course, notice, strictly speaking, I have not said I don't care about a behavior. The way I have defined it, I have said because it's a polynomial time randomized algorithm, something is a polynomial time randomized algorithm only if it runs on a fixed polynomial time on every input, even on the don't care inputs. But that's easy to this one. That is an algorithm, you just keep a counter, and if it ever crosses this time bound, you stop it. So whether it's a S instance, no instance, or don't, that's an easy thing to do. That's not a hard thing. So this is all I mean by promise BPP. And there's a technical reason why we would need this. I do not know if I will be able to come to why we'll have to work with promise BPP rather than BPP. So is the decision, is promise BPP clear to what I mean by promise BPP? So what we will now do is, instead of creating a complete problem, certainly if I manage to remove randomness for promise BPP, so certainly this should be an easy observation. BPP is contained in promise BPP. That's trivial. So certainly, if I want to eliminate randomness in BPP, if I could really eliminate randomness with promise BPP, that will also be eliminating randomness from BPP. So what we want to do is, I'm going to look at what we're next going to do is look at a complete problem for promise BPP. So sort of what I will call a complete problem for promise BPP. And for this, it will be useful for me to define one more notion. So far, we have talked about something called algorithms. I will now talk about something called circuits. What's a circuit? A circuit is just exactly what you think it is. It is sort of an object with OR inputs and gates, possibly a NOT gate in between, and then OR gates again. And it's something like this, and it could, this NOT gate, it could feed into this one. It's sort of strictly speaking, it's a directed acyclic graph in which the bottom layer is the inputs, x1 to xn. These are the inputs feeding into this one, and then you feed it and you compute these ORs and NOTs and compute the function. This is what a circuit is. And there will be two things about a circuit which we will talk about. One is the depth of a circuit. So by the way, a circuit computes a function. It's going to take an input of length n, and the only permissible gates I'm going to allow are it's a NOT gate. This has fan in 1, an AND gate, and 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 OR gates. These have arbitrary fanning. And the fan out of each gate can be as large as possible. What does fan out mean? Fan out is this, for example, this particular NOT, you have computed some function over here. I'm using it for this gate as well as I'm using it for this gate. You can reuse, that's what out. And the fan out is arbitrary. Fan out is arbitrary again. And it has and we'll be interested in things in which there's a single output gate. In this case, this is the output gate. And this computes some function on the inputs. So the depth is the length of the longest path from any input layer all the way to the output. That's what the depth is. Depth is not a thing which we will be working with. Size is a more interesting. This one, size is the number of gates in the circuit. So this is what a circuit is. Why am I talking about circuits? The nice thing about circuits is, if tell me a particular, notice circuits take up inputs of particular length, and then they tell you what is the function being computed on inputs of this particular length. This is slightly different from algorithms. Algorithms take inputs of arbitrary length and they will compute. So algorithm is more like, well, in some sense corresponds to a family of circuits. It's a circuit for every input length. It tells you, if you give me an input length 10, it's going to give you a particular, hidden in that algorithm is a circuit. If you give me an input length 100, there's another such circuit. So this is an algorithm corresponds to a family of circuits, but a circuit is just sort of an algorithm narrowed down, sort of restricted to an input of a particular length, which is the number of input bits that is fed to the circuit. So it's not hard to see, I will not do this, but it's not hard to see that if a particular promise problem pi has an algorithm, there's a deterministic algorithm is what I want to say, has a deterministic algorithm running in time tn, that on inputs of length tn, then it's not hard to see that for all n, there exists a circuit Cn that of size possibly order Tn log Tn. Actually, let's not write this, something like almost the size of Tn that computes pi restricted to inputs of length n. That is, you can just take the algorithm, you can go into the belly of the algorithm and find out what the circuit it computes, and that circuit will have so many gates. So each gate corresponds to the running, each step taken by the algorithm. This is not hard to see. And why as computer scientists sometimes we look at circuit, it's sort of, we would like to analyze how algorithms run. It looks at the guts of the algorithm. It opens up the algorithm and writes down, this is exactly what the algorithm is. And can I analyze an algorithm? This is how it's sort of opening out the algorithm. So it's sometimes useful to look at circuits. Anyway, right now, why am I looking at circuit? Because I'm going to define the complete problem for BPP based on circuits. So is the definition of circuit clear? And circuits, the complexity of a circuit for us, there will be n input gates, there will be one output gate. It's a directed acyclic graph. And the size of the circuit is basically the number of gates in the circuit. So now I'm going to give you, now, given a circuit, so C, we're going to talk about mu of C. Mu of C is just the fraction of inputs on which the circuit is going to take the value 1. So it's basically, it's the set of all x in 0, 1 to the n, such that C of x is equal to 1 by 2 power n.
In the earlier result, why is 0, 1 power n being removed, like pi complement of 0, 1 power n?
Sorry, I didn't follow.
So in the above proposition above, like
Okay.
which is, if there is a deterministic algorithm, then you have a circuit of size OTN,
Yes.
right?
Yeah.
Why have you removed 0, 1?
Sorry,
I have
that's
not removed. I have restricted. Pi is something on sigma star. I have on 0, 1 star. I'm just restricting my attention to inputs of length n.
Oh, okay. Sorry.
Yeah, okay. Let me. What I mean here is this is restriction, because this circuit can't work on inputs of smaller or larger length.
Right. Yeah.
Okay. That's all I mean over there. It's not. That's not set difference. That is restriction. So mu of C is this. Okay. Given a circuit, I can do this. Now let's ask the following thing. Now let's go back to, suppose I have a promise. I have a promise problem pi. I have a promise problem pi in promise BPP. So in particular, that means there is a randomized algorithm A that has the right features. That is, on S instances, it A of the probability it accepts is 2/3, or no instances the probability accepts is 1/3. It's at most 1/3. So what do we have here? Now you can look at this randomized algorithm. Let's take a particular instance, which is either an S instance or a no instance. I don't care which of the two instances. It's not a don't care instance. You can look at the algorithm now, in which you hardwire. You can look at A restricted to just this particular input. The random input, I'm not fixed it. I have fixed the actual input. So the algorithm A itself looks like this. The algorithm A for us, it has the real input X, it has the random input R, and then it's going to compute some A of XR. This is how the algorithm is. Now what I have done is I'm looking at AX, which is basically this is the only variable thing. I'm looking at the new function, which A of X, comma, this one is a function from 0, 1, M to 0, 1. Agreed? For every random coin, it tells you whether it accepts or not. Now you can look at the circuit corresponding to this particular thing. So by this previous thing, I can now talk of the C of X. C of X is the corresponding circuit. Okay, and it's a circuit which is also a function. Notice there's a circuit for every input X. For each input X, there's a different circuit whose input, the input of this circuit is not the actual input X, but actually the random coins. And what do we know of this? We know that if X is in pi Y, then mu of C of X is greater than 2/3. If X is in pi no, then mu of C of X is less than 1/3. I've done nothing. I've just set up all notation to rewrite the same stuff which we've been talking about. There's nothing that's happened so far. Okay. So given a randomized algorithm or problem in BPP, there's an underlying algorithm here. I can talk about the circuit, and there's a different circuit for every input length over here. Actually, this is the reason why we are talking about circuits. There's something non-uniform here, but let's not get into this. I'm just so if you follow this so far, now I'm going to define. I haven't yet. All of this is to define what the complete problem is. The complete problem is the following problem, which I will call plus.
So this is with the uniform distribution, right?
Yeah. So the way I have defined mu of C is always with the uniform distribution. Look at this.
Yeah, so the random bits, I just wanted to confirm that the random bits are all completely...
We have always defined random bits to be random coins, therefore they are uniform distribution.
Oh, okay.
Yeah. Okay.
As in, normally the right mu is with respect to the uniform distribution, but you are trying to come up with things that are not random and still get close to the right answer.
Right answer.
But you're always comparing with the uniform distribution.
So what is it? So what is the problem of promise BPP? You given an input X, you can look at this algorithm A, and look at the algorithm A, you can come up with this AX, and hence you can come up with the circuit CX. What you need to determine is mu of CX greater than 2/3, mu of CX less than 1/3. If you can tell which of these two cases it is in, you know if X is a S instance or no instance. You need not run the randomized algorithm to do it. You use the algorithm to construct C of X, and then you ask, is mu of C of X greater than 2/3 or mu of C of X less than 1/3? If you can do it in a different way without tossing random coins, that solves the problem of the BPP for us. So that's why that sort of tail says this is the sort of problem I want to be talking about. It's called the approximate circuit valve. So it's a promise problem. Which I will call CAY epsilon. So there is an underlying epsilon. So there's an underlying input length. In the input length, there's an input length is, there are two things which is input length. The circuit input length will denoted by M. And there's an underlying epsilon which is in 0, 1. CA epsilon, it has two parts in, sorry, CA epsilon, circuit approximation. It has set of S instances and no instances. And what are the S instances? The S instances are a pair C comma P. So C is a circuit, P is a number between 0 and 1, and it is such that mu of C is greater than or equal to P plus epsilon. So it is, I accept those, the S instances are those circuits whose acceptance, whose fraction of accept instances is greater than P plus epsilon. It's greater than P by a margin, P plus epsilon. And to make it symmetric and to symmetrically, the no instance is going to be the same object mu C less than or equal to P minus epsilon. And notice this is a promise problem because there are some C's and P's for which the value will be between P minus epsilon and P plus epsilon. I don't care what happens to those instances. This is the S instances, no instances. Clearly, it's a disjoint set of things, and it's this one. And this is my problem. And so, is a statement of this one clear? There must be a few things that should be easy observations that we should be able to immediately make from this. One, is this problem in promise BPP? Is there an algorithm for this? Think of epsilon as a constant. Think of epsilon as a constant. Is there an algorithm for this? So I give you CP. How do you find out, or rather, is there a randomized algorithm for this?
Yeah, actually tossing the coins, right?
Yeah, you just given a circuit, you just pick a few random coins, check if it is one. If it's one, you accept with probability 1. If it is 0, you reject it. And there's a gap between. In the yes case, you accept with probability P plus epsilon. In the no case, you reject with probability P minus epsilon. And we saw how to use Chernoff bound to amplify this gap. We saw how to do this. Therefore, actually, it's easy to see that this plus epsilon approximate value, circuit value, is in promise BPP. Okay, it's in promise BPP. Now I want to say another thing. It's not just in promise BPP. I sort of want to say it captures the hardness of promise BPP in a very nice fashion. I want to say, suppose CA epsilon was, you were able to give a different deterministic algorithm for CA epsilon for this promise problem. I claim the way we defined it, all the motivation that I set up will show you that actually entire BPP falls in promise B. Do you see that?
What is promise P?
Promise P is once again, P is the set of languages. Promise P is the set of promise problems which have a deterministic algorithm that distinguish the S instance from the no. The polynomial time deterministic algorithm. It's the same. So every class which we define, we can define the corresponding promise problem in which the inputs are now not languages, but promise problems. The reason I have to say CA epsilon is in promise P is CA epsilon is not in P. CA epsilon is not a language. CA epsilon is a promise problem. So I can't say CA epsilon is P. This is just shorthand for stating there's a deterministic, suppose there's a deterministic polynomial time algorithm that distinguishes the S instances from no instances. This is just shorthand for me to avoid writing that long statement.
This is because that statement that we said that if we have a deterministic algorithm, then we can construct circuits.
Yeah. So how would you do this? Suppose I give you some problem. This is exactly what we did here. Suppose I give you some problem in promise PPP. There's an underlying algorithm to it. You have access to this algorithm. From this algorithm, you can compute this circuit C of x. For every input x, you can compute the circuit C of x. And all you need to check is mu of C of x is greater than 2/3 or mu of C of x is less than 1/3. So you can now feed, say, C of x comma sort of half. You can set epsilon to be 1/10 and say C of x comma half. That in the S case will give you. So that says all I want to claim is if you. So the proof for 2 is just the following. Proof of 2 is, suppose you have some problem from this BPP that implies there exists an algorithm A, a randomized algorithm A. That also we saw that implies there exists for all inputs x, there exists a circuit C of x such that mu of C of x is greater than 2/3 if x is in pi y, and mu of C of x is less than 1/3 if x is in pi n. So in particular, that hence C of x comma half is in CA, say 1/10, and if x is in pi y, and C of x comma half is in, sorry, S instance of this. Did I flip the order of this? Which way was yes? It was no. CA 1/10 yes instance, and CA 1/10 no instance if x is in pi. So you could now now you know that if x is in the line, so you have these two. Now you can run the promise P algorithm. You can use the promise P algorithm for CA. Use promise P algorithm for CA 1/10 to determine if x is in pi y or x is in pi. Notice I have not this algorithm has not tossed any random points. I have solved promise PPP without tossing any random points because it took the randomized algorithm. It took the randomized algorithm over here, but it didn't. It just constructed the circuit from the randomized algorithm. It didn't actually toss any random points. And but that circuit had this property. It had this distinguishing property. Hence, it has. I'm just rewriting that property this way. Now it used the deterministic algorithm for CA epsilon. It used this algorithm to determine whether it falls in this case or this case. And that was able to distinguish the two things. So all I'm saying is, there's a reason why I defined this problem. CA epsilon is sort of a prototype complete problem for promise BPP. If it falls into promise P, it brings along with it all of promise BPP into promise P. So to understand if promise BPP is equal to promise P, it's sufficient if I work with just this particular problem. In particular, if promise BPP equal to promise P, this particular problem has to be in promise P. But if this particular problem is, everything else is also. In that sense, it's a prototype complete problem for promise BPP. People with me?
So Prahladh, actually the first observation also I'm a bit confused. Like
Which observation?
The first one, that it belongs to promise PPP.
Yeah. So why is it? Let's stare at the definition for it. I give you a circuit and I give you a P. Okay, I give you a P. That's the input. What's the algorithm that you will do? You just pick a random input to this circuit and see whether it's an accepting input or a rejecting input. The circuit outputs 1 or 0. If it outputs 1, I'm going to say yes. If it outputs no, I'm going to say 0. Now, what's the probability that this circuit is outputting yes? It's P plus epsilon in the yes case. And what's the probability that it's outputting yes? In the no case, it's at most P minus epsilon. Is so much clear? Is so much fine?
Yes, yes.
So in the yes case, we know the probability of acceptance is at least 2/3. In the no case, the probability of acceptance is at most, in the yes case, the probability of acceptance is at least p plus epsilon. In the no case, the probability of acceptance is at most p minus epsilon. Okay?
Yeah.
So this is just almost like BPP's definition. In BPP, you had 2/3 and 1/3. Here you have p plus epsilon and p minus epsilon. That's the only difference.
Right. Okay. Got it.
And you can use like a now Chernoff bound or something to amplify this gap.
Okay.
Because there is a gap between the two cases, you can now use a Chernoff bound like thing to amplify the gap. That's all. Does that answer your question?
Yes. Yes.
Okay. Any more questions?
Yes. So in the definition of CA epsilon,
Yeah.
P could be anything.
P could be anything. So we think of P ideally P could be anything. So P could be any number. So because it's an input, it has to be written in binary, and we expect it to. You are giving it with some precision. Yes.
Okay. And second question is, so CA epsilon is in promise P. If it is in promise P, it brings along with it a lot of problems to promise P, right? This is what you said.
Yes.
Now,
yes.
So is this is probably not the only problem which is like this. There are
No. So there are several candidate problems. So usually complete problems don't exist in isolation. A whole bunch of problems will be complete. Yeah.
Okay, so it's like some sort of equivalence class of problems which are all complete, or there are.
Yes. You can build. Yeah, they will be. So if you, in fact, a fair amount of the complexity course is you take a particular complexity class, we identify one complete problem, and then we identify a whole bunch of other complete problems. These are all, that is, they are all sink or swim together. Even if one of them falls in the lower class, everything else falls. Even if one of them does not fall, everything else will not fall. So there's a sort of an equivalence class of problems. This is something, in fact, this if you any complexity course, this is what we'll do for every complexity class. We'll try to understand a complete problem so that we can, to study the class, it's sufficient to focus your attention on this complete problem. Sometimes you might not like this complete problem, you might work with another complete problem. This is a problem which is almost follows from the definition of BPP. That's why I written it, but there are other problems.
Okay, so for example, over here, all the complete problems which bring promise BPP to promise P,
Yeah.
they form some sort of equivalence class.
We could bring yes. You could bring this one. There is a notion of something called a reduction. The way to do this, a reduction is basically when does one problem reduce to another, and that will determine the equivalence class. Yes.
Yeah. Okay. Thanks.
Okay. Any other questions? Okay. So the reason I spent a lot of time on promise problems is we will be dealing with promise problems a lot, and sometimes when we want to talk about BPP, we want to de-randomize BPP. We won't talk about all of BPP. We'll just work with this one particular problem. Because if I manage to de-randomize this particular problem, to remove randomness in this problem, observation 1 tells you a natural way to do it is use randomness. Observation 2 tells you if you manage to do it without randomness, then not only does this problem, but all of BPP collapse to P. In fact, that's the reason I defined this class, was primarily for these two reasons. This is the most important. This observation is the reason why this whole definition was done.
So for observation 1, right? This approximate circuit value problem is in promise BPP. So to belong to the class promise BPP, you need a randomized algorithm with, like, say, polytime and all the probability bounds and stuff. Right?
Yes. So
for this particular problem, what is the algorithm?
The algorithm is just this. There's one algorithm. If in the yes case, which will accept with probability p plus epsilon. So what's the algorithm? The algorithm is just pick a random input for the circuit, run the circuit on that input, and accept if the circuit outputs 1, reject if the circuit outputs 0. That's the algorithm. Certainly, it's polynomial. The number of randomness is exactly the input length of the circuit. So it's polytime in the circuit size. Its running time is exactly the description of the circuit, because you have to run each gate and output it. So its running time is, in fact, linear in the size of this one. So it's a polynomial time algorithm in the input length. Okay. And then, of course, you have to do this comparison. That's all. That's all is the algorithm. The only, why is it not in promise BPP? why is this algorithm not yet in promise BPP? In the yes case, it accepts with probability p plus epsilon. In the no case, it accepts with probability at most p minus epsilon. You might want to make this gap larger. Then you just run this algorithm several times over and use Chernoff bound or the pairwise independence, one of them, to make this gap larger. Right now, the gap is only 2 epsilon. You can make this gap like 1/3, like 2/3, 1/3, or whatever, by repeating it several times. Okay. Much slower than what I had. But all of this is clear so far. Okay. Now I'm going to go to another topic which we have been talking about, sampling. We're going to abstract out what we did with sampling so far. So what was sampling? I'm going to sort of pictorially say what sampling was. You had, so what was the problem in sampling? There was an oracle F given on 01M to 01. For reasons that will soon be clear, I'm going to change the notation from M to N from now onwards in the course. So there's an oracle, sorry, and this was not actually not a 01 oracle, it was possibly return a real number. And the goal was to estimate an epsilon additive approximation of mu of f with high probability. That was the sampling. And this was the goal of the thing, and sampling was one way to do it. And what was sampling doing? Sampling, you can think of it as there is this underlying space 01 to the n. So the function is being defined on every such point in this space. And what was sampling doing? Each time you picked, sampler was, you picked a set of t vertices, t these points, took their average, output it. You could have chosen a different set of random points, you pick a different set of t. This is in the case of the independent sampler, each of these were t size sets in the way we had done it. Just keep your example of the independent sampler and the pairwise independent sampler in mind. In the case of the independent sampler, we had and these are the points which the independent sampler had queried. T fully independent points. So the independent sampler, these sort of circles which I'm drawing, where every subset of t things were a part of them. They were in fact 01 to the n. So we will call this n. In the independent case, sorry, just n. I'm going to identify this with n. In the independent case, we had all t tuples of 01 to the n were possible things in the independent sampler. Pairwise independent, it was not all tuples, but a much smaller set. We got this. Now we're going to say a sampler is any object of this type. A sampler. So this is how I'm going to define a sampler. Sampler is a hypergraph of this type. A hypergraph is just a hypergraph in which the vertices, so it's a hypergraph G. Let's call it a sampler, so it's a hypergraph H. The vertices and a set of edges. What are the vertices? The vertices B is exactly this n, which we identified it as 01 to the n. And F is some subset of n choose t. It's these hyper edges. They could be ordered sets, unordered sets. I'm not going to make a fuss, so this could be actually, it could be n choose t rather than this one. I'm not going. You could define it whichever way you want it, right? I'm not going to this one. And furthermore, for all edges in F, there was some function he going from 0, 1 to the t to 0, 1, which sort of looked at the value of the function on these t locations and output a candidate value. Usually it was the average. It just took the average value of these guys and output it. Typically, he is just the average function.
So that's a curly braces, right? On the 0, 1 to the t.
Which 0, 1 to the t?
He, the domain.
No, he takes the value of the function on the t tuples. So it takes the t real numbers and then outputs another real number.
Okay.
What the sampler did, it queried the function at these t places, got values, and then took the average of those values. So he usually is the averaging function. Okay. So a sampler is this hypergraph and this family of edges. He going for all E in F. So a sampler is given by this object. This is what a sampler is, such that it should have the following property, such that for all functions F from 0, 1 n to 0, 1, the probability that if you pick a random edge in the sampler and applied he on the vertices in that edge, take the value of the function, this one, minus mu of F, the probability that this is deviates by more than epsilon from the mean is less than or equal to delta. Then this is why we call it a delta epsilon sample. This is a lot of notation for something which you've already seen so far. But is it clear what I have defined? This is just an abstraction of the independent sampler and the pairwise independent sampler that we have seen. So both these samplers, the underlying set of vertices is the set of random points, the 0, 1 to the m. I've changed notation. I'm going to call it 0, 1 to the n. And the sampler is picking up the sampler is sort of picking hyper edges in this, such that it is estimating the global average by some function on the, it's going to take a hyper edge, it's going to look at the function locally only within the values within the hyper edge, and based on that, it's going to compute some function. Almost always it's the averaging function. And based on that, it's going to output a value. That averaging function should be, sorry, this is V in E. V in E. These are the edges in E. Apply the function E. And this local average, so this is what I will call the local average. This local average should not deviate from the global average by more than an epsilon fraction. The probability that it deviates should be at most delta. Such a hypergraph is called a delta epsilon sample.
Can you explain again how the hyper edge is being represented as input to HE?
So it's not. So what is the hyper edge? So H. So I have a, let's look at it. So I have a hyper edge. An edge looks like V1, V2, VT. An edge looks like V1, V2, VT. Now the sampler is going to query the function at V1, FV1, FV2, FVT, and it's just going to apply HE on this tuple. That's all I mean.
Okay. Can you show again the definition of the function f? Okay, f is just some function which takes an n-length string and gives a 0, 1 real number. Okay.
Yeah.
Thanks.
Yeah, it's a formalism. It's a long formalism of a concept. I think if you know the independent sampler and pairwise independent sampler, this formalism is just the abstraction of this object. What we want, I'll come to what you want, but this should sort of, so in both the independent sampler and the pairwise independent sampler, the set of vertices is always a set of random points. The hyper edges, what were the hyper edges were different in both cases. In the independent sampler, you had all possible t tuples as hyper edges. In the case of independent, this one, f was actually equal to n to the t or n choose t, depending on whether it's with repetition or without repetition. Pairwise independent is a much smaller collection of this, but yet, and in both cases, he was just the averaging function. He took t numbers and outputted their average, but it need not do this. It could do some other complicated function on it. Both the examples we saw was this, but it had the property that For every function f, this local average you compute on the hyperedge deviates from the global average by more than an additive error epsilon with more than an additive deviation of epsilon with probability at most delta, where delta, this probability is over the choice of the hyperedge. Somebody had a question.
No, I'm unfamiliar with this notion of a hypergraph. Like, how is it a generalization of a graph?
So the only difference between a hypergraph and a graph is the following. A graph, there's a bunch of vertices and a bunch of edges. And what are edges? Edges is a subset of n choose 2, the vertex choose 2, because every edge is a pair of vertices.
Okay.
This is just every edge is a t-tuple.
But a collection of vertices.
Collection of vertices. Okay. So it's a T uniform. So let's call this as a it's a T uniform hypergraph.
T uniform means all the edges have T vertices.
Yeah, but a hypergraph need not have. Hypergraph could have arbitrary. It's just a collection. It's a set system in some sense. It's a set system. So sometimes people don't call it hypergraph. They will usually also, this is sometimes represented as a bipartite graph in which this side is N, this side is the M, the edges. These are what we call the hyperedges. For you have a vertex for every hyperedge here, you have a vertex for every N, and you connect a hyperedge to the T edges, T vertices that participate. A hypergraph can also be represented as a bipartite graph in the most natural way. Okay. Sometimes a sampler is described this way. Sometimes you describe it as a hypergraph. You could do both. Okay. Both
I have a question.
Sure.
I want to see how this is an instantiation, or rather an instantiation of this is the pairwise independent sampler. So okay. I think what we're trying to say is that suppose I have such a hypergraph, then once
I want to say a pairwise independent sampler is one such hypergraph.
One such, yeah. So so I'm trying to see how. So what we want is a hypergraph such that if I choose the edges of the hypergraph uniformly, then the distribution that I get on the set of vertices via that distribution is pairwise independent.
Yes, and this is exactly so. So this collection. So if you recall, the pairwise independent set was we defined this collection of, you picked A and B at random. Assume now 0, 1 to the n is actually GF2 to the n. This one, and you had a hyperedge for every pair AB.
Yeah.
For every pair AB, and what are the points in the hyper? So for every pair AB, you have a hyperedge. Therefore, there are 0, 1 to the 2n number of hyperedges. And what are the vertices in the hyperedge corresponding to AB? It's A of alpha plus B for every alpha in the field.
Yeah. Okay.
Yeah. So this will be sort of, I think I made some mess with some of the notation, but that will be the pairwise independent sampler. Okay. Any questions so far? It's a formalism, but the reason I'm going to give this formalism is this object is, what do we want of this object? So let's make some more observations and some remarks which I want. So sometimes samplers are expressed as bipartite graphs, sometimes samplers are expressed as hypergraphs, and they are the same notion. Hypergraph and a bipartite graph is the same thing. You just bipartite graph represents a hypergraph by just putting all the edges as vertices on the other side, and you put the edges in the bipartite graph only if this particular hyperedge contains the vertex. It's just a bipartite graph representation of a hypergraph. Okay. And by the way, an excellent source for understanding about this one is, there's an article by Odette Goldreich called A Sampler of Samplers, and there's a lot of questions of things. It's a very good collection of resource on samplers. It tells you everything that we know about samplers and the current open problems. It's a little old, but no progress has happened with respect to samplers since this survey was written. It's a very nice survey due to Odette Goldreich. So if you're looking at it, if you want to know more about samplers, this is a good source to look at. It's called A Sampler of Samplers. Okay, so let's make some more remarks. If the function he is the averaging function, which it was in our case, then we'll call the sampler an averaging sampler. And later on, we'll ask what other samplers can be, what else can you do? We will see later on, they will actually construct non-averaging samplers, which will perform better than averaging samplers, surprisingly, at least. But there are current constructions in which the non-averaging samplers outperform the averaging samplers. 2, if so this is the condition, star. If star holds only for Boolean functions, that is f going from 0, 1, n to 0, 1, not 0, 1, not the range. The range is just 2 points, not the entire interval 0, 1. Then we'll refer to it as a Boolean sampler. Okay, because sometimes we might be able to any sampler is a Boolean sampler certainly, but sometimes it might be easier to construct Boolean samplers over full-time samplers which work for any 0, 1 valued function. That's one point. The third point, which is the most needed point for us, is we want the sampler to somehow be efficient. In what sense it has to be efficient? That is, the sampler should have this property. Notice in both the pairwise independent, I tell it the edge label, I tell it which edge I'm operating on and which vertex in that edge I want to. It must be able to find out which is that vertex. So it must be given E in edge, that is given E in M, that is the edge label, and I in T, can compute Vi in time, polynomial in log of M and log of T. So in the log of it should be, that is polynomial in its, that is poly in the input, poly in the input. This should be given the identity of the hyperedge. You must be able to, from the hyperedge, and I tell you, I want the 10th vertex the hyperedge. You must be able to, from the label of the hyperedge, you must be able to find out the 10th vertex efficiently. Notice in the case of independent sampler, this is very clear. The identity of hyperedge reveals out all the T vertices in it. In the case of pairwise, the identity of a hyperedge, at least the construction we saw, reveals only the identity of hyperedge is just these two elements, A and B. And from that, you need to find the 10th element. But that was an efficient process because field operations were efficient and all of this. So we want a sampler to have this property, but we also want the sampler to be efficient. Whichever samplers we construct, all samplers which we construct, it will be easy to show that samplers exist. The hard part will be to construct samplers which are efficient. In fact, you pick a random graph of this size, it will be a good sample. What do I mean by random graph? No, let's go back to it. What was the difference between the pairwise independent sampler and independent sampler? By the way, let's take a minute back. Are people comfortable with this definition of sampler, this abstraction of the independent sampler and pairwise independent samplers? If not, we will take a few more questions in, because I need this to go to the next topic, the expanders. Okay, so that's fine. So what are these both samplers? You have this set of 0, 1 to the n, this space, and there are hyper edges sitting here. And you want these hyper edges to have this property that if you take the average, somehow let's assume that the HE function is always the averaging. The local average on each of the hyper edges, for most hyper edges, actually are very close to the global average. So these sort of hyperedges sort of very nicely compute it, the global average. This is what I want of the sampler. This one. Question is, can we construct such samplers? Now let's see how does the pairwise independent sampler and the independent sampler differ from each other. The pairwise independent sampler has far fewer hyperedges than the independent sampler. The independent sampler had something like n to the power p hyperedges, whereas the pairwise independent sampler had only something like n square hyperedges. It was a much smaller set of hyperedges. And our goal in trying to construct samplers will be to construct a sampler hypergraph with as few hyperedges as possible that still computes such that the local average does not deviate from the global average. With for most cases, the local average for most hyperedges, the local average is very close to the global average. This is what we want, and the goal is to construct, in the case of samplers, the goal is to construct efficient samplers with as few hyperedges as possible. Okay, that's one thing which you would like to do. If we can construct such a sampler, then we can try to reduce the amount of error. Samplers, notice both the independent sampler and the pairwise independent sampler were used to pairwise independent sampler reduce the amount of extra randomness you needed in doing error reduction for BPP algorithms. Now, if you want to do error reduction even in a more de-randomized fashion, having even a sampler with even few hyperedges will then actually the number of hyperedges is exactly the number of random points needed by the error reduction algorithm. You can look at that a little bit and realize it. But what I want right now is a sampler, an efficient sampler with as few hyperedges as possible. This is what we care for. So is the definition of sampler clear and the goal that we are pursuing? Okay. Silence because people have lost everybody, or things are clear. So yes, no, don't care will be useful at this point of time.
I think I follow.
Okay, fair enough. Okay. Okay. So I'll address the yes, no. I can't address the don't care. That's one. Anyway, so how do we construct such a? The question is now, how do we construct? That's our goal. This is the goal which I want to do. And this goal will take us to a different object.
Could you explain what it means to be efficient here in this context?
So efficient means that is given the input length and the time t. The point is the sampler is trying to compute the average, or the global average in some sense. So the sampler, I want the sampler given an identity of the hyperedge. So given an e in 1 to m. So I give you a number from 1 to m. I tell you the 115th edge. Tell me the 10th vertex in the 115th edge. You must be able to find out this in time, which is polynomial in the number of edges, in the length of description of the edges, and the time and the length of description of which vertex it is. That's what I mean by polynomial.
Oh, okay. And so I think you maybe gave an example in the case of like pairwise sampler, right? Like yes. In that case, t equal to 2, right?
No. T is not equal to, t was equal to n. It's the identity of a hyperedge was just two field elements. Yes. But the number of things in the sample, t was the number of samples. You actually produced several samples. You produced as many samples as the size of the field. The identity, so if you go back to the pairwise independent one, the hyperedge corresponded to a line in the, the line, that was the identity of a hyperedge. But what were the samples in it? There were all the points on the line were the samples. So t there was the number of points on the line.
So, but t is the number of vertices in the hyperedge, right?
T is the number of vertices. Those were the, if you recall, that was how those are the vertices in the hyperedge. So if you view, so if you want to go the pairwise independent, now the vertices, so the pairwise independent sampler, the construction AX plus B, this object over here, this guy over here, this rectangular object, rectangular or skew rectangular object, is the set of points in the plane F square.
Okay.
And every hyperedge is the set of, every hyperedge corresponds to a line, an affine line.
Okay.
So an identity of a hyperedge is A and B, the slope and the y-intercept. And what are the points in it? It's all the points on the line. And we showed that these guys mix well. These guys, if you take an average on a particular...
Just to add a little bit to this or something, I mean, think of, it's always good to compare what the standard like Chernoff bound average sampler does versus what the pairwise independent sampler does. So every run of the sampler, I mean, you're given some function that you're trying to compute the average of. So what you would be doing is you would be sampling a bunch of points and then computing some aggregate. The aggregate is given by the HE. And the set of points that you sample is given by this V1, V2 till Vt, which we are now calling a hyperedge. So the E refers to one run of your sampler. Like every run of your sampler will go and query a bunch of things and then take its average. Now, what is happening in the standard Chernoff bound averaging sampler? Each such E is very few vertices. I mean, the number of samples you typically take is far fewer, but there are lots of hyperedges in your thing. I mean, the number of hyperedges sort of correspond to how many random bits you use or how many different runs you have. Whereas in the pairwise independent sampler, each hyperedge is a little fat or it's wide, but the number of things are fewer. So that's, you're sort of trying to trade off, you're trying to have as few hyperedges as possible typically, but still somehow give similar guarantees.
So how do we achieve this goal of achieving as few hyperedges? So we have this object. This was the base object for us, 0, 1 to the n, which we identified with n, sort of verification. We want to sort of build these sort of clouds over here, such that, and let's think of just the averaging samplers. Let's not talk so more than, such that the average within each cloud was very close to the globe. Most clouds have the property that the local average is close to the global average. This is what we want. So somehow these clouds should be smeared. They can't be in any one part of the space, because they are, most of them are in one part of the space. They will not. The average could for the function could be coming from elsewhere in the space. So we need this property. So what we will sort of do is, how do we construct such objects? We will sort of think. We're going to go back to regular graphs, not hypergraphs. We're going to think of this. We're going to think of a graph whose vertex set is n. So we're going to think of an underlying graph. We're going to we're just going to superimpose a graph on this set of points. We're going to superimpose a graph, and then what do we want of this graph? And from a graph, how can we construct these clouds? There are several ways to construct these clouds. You can say a cloud is I need to construct clouds of length t. What do I want? There are clouds of size t. One way how to take it, take walks of length t in this graph, and you could say each walk I will think of it as a cloud in this graph. So walks of length t. Walks of length t. That's one possibility. Other possibility is you take a vertex and just take a small ball of all vertices, take one step around it, take 2 steps around it, take a balls around each vertex, and take balls of size t around all the vertices. Okay, this is one way of, if I have given a graph, how do I come up with clouds of size t? These are various ways in which I can come up with clouds of size t given a graph like this. Notice that the independent set sampler is exactly the first. independent set sampler is the case in which the graph is the complete graph on n vertices, and the t things are a walk of length n, t. The independent set is exactly, the independent set sampler is the case in which the graph is the complete graph on n vertices with also self loops, and the t vertices is just a walk of, is all possible walks of length t. That's the independent set sampler.
Sorry, what do you mean by independent set sampler?
Sorry, the independent sampler, the independent sampler, the independent sampler, not an independent set, the independent sampler. The independent sampler is exactly this object. Now, question is, okay, say, why are we doing this? I don't know this one. I want to construct samplers with good properties. So I want graphs such that either walks of length t or balls of size t around each vertex. Where did I put around each vertex? These sort of have this property that the local average is close to the global average. Now, if you ask all of this, now question is, what graphs have this property? You can ask which graphs have this property that either the first kind of clouds or the second kind of clouds are good samplers. This is what we're going to ask. Certainly the complete graph, we saw the complete graph, the Chernoff bound tells you that walks of the first type are actually good clouds. That corresponding graph is a good sample. But notice that this graph, in this case, the number of random points, the number of hyperedges in a complete graph is way too much. It's n to the power t, because that's one. I want a graph which is much, much small, the hyperedges to be much smaller. So suppose this graph, furthermore, the degree of the graph was bounded. Degree of this graph is bounded. Say d, and d is substantially smaller than n, possibly even a constant. Okay, then how many walks of length t are there? So suppose a graph has degree d. What's the number of walks of length t?
d to the power t.
It's n. You have to choose the starting vertex and then d to the t minus 1.
Right.
Okay.
Yeah.
That's the number of walks of length t. Notice this is substantially smaller than n to the power t if d is much, much smaller than n. What about the number of clouds, number of balls of size t? This is exactly n. This is even better. It's just n. It's not even n square like what the pairwise independent object was. It's n. So if I could come up with a graph such that these to the walks of length t and the balls of size t had this property that the local averages were as good as the global averages for most of objects of this type, then these will be much better samplers than what we have seen so far. The dependence on n is even better than the dependence on n in pairwise independent samples. The dependence on n is just, there's just one, it's just log n. There's just n, it's not n square. So independent sampler, the number of hyperedges was n to the power t. The independent sampler had the pairwise independent sampler had n to the n square, and these have lower than both of them. If I manage to construct a graph D which has this property. Now, what are such graphs? It's unclear if such graphs exist. So these graphs, somehow these graphs should mix well. There are various notions in which you can define. Do such graphs exist? Do such graphs exist? What do I mean by that? Constant degree graphs, ideally constant degree graphs. That have the property that have local average. I'm being very informal here, is equal to global average for all functions, yes. Do such graphs exist? If such graphs exist, then you can give rise to such samplers. Now we need to make this property a little more precise. It's a very vague property. What property of the graph will give you this? There are various notions. There is, say, as a graph as a vertex expander. I'll define some of these notions. Vertex expansion, edge expansion. There are various attempts to define this. The random walk mixes well. There are different communities. This problem has appeared in multiple communities, and each community has actually tried to abstract this as what a concrete property is, or possibly random walk mixes well, or some notion of quasi randomness in the graph. And there have been various attempts to sort of formalize this very vague statement. This one. And strangely enough, it happened to be that all of these formalisms actually lead to the same object, which is what we're going to call expanders. And that's what we'll see. There's yet another definition called spectral expansion. And strangely enough, all of these led to the same object, which are today called expanders. And so they were discovered multiple times in this one. I think one of the earliest is Bogdan and Kolmogorov, when they were trying to understand neural networks in the brain, how they are connected, and they wanted the brain to be well connected. That's how they came up with it. Pinsker, who was working at AT&T, wanted to talk about telephone networks and wanted to understand how these telephone networks should be led. He came about for this. So there's been this graph, this notion of an expander has happened by different communities in the computer science and electrical engineering, this one independently, and we will talk about some of these notions. All eventually lead to the same object, which we'll call expanders. And what I will do is I'll actually define this object now, ask 3 questions, and we'll attempt or try to answer these questions in the next one. So we're going to take the first approach. We're going to talk about vertex expansion. So let's say a graph G equals VE, where V, the size of V is N. Now this is the reason why I shifted from M to N in the previous thing, because I want to always call the size number of vertices in a graph to be N. That's why I made the shift from M to N. Sort of it's unholy to call the number of vertices M. Is a KA vertex expander where K is an integer between 1 and n, and A is some real number greater than or equal to 1. If for all sets S of the vertices, if the size of S is at most K, then the size of the neighborhood of S is greater than the size of S by at least a factor K. So once again, let's draw it pictorially. So what is N of S? N of S is a set of all V in vertices such that there exists a U in S such that UV is an edge. So it's a set of all neighbors of S. So you take any set S and you look at its neighborhood. That's N of S. The claim is the neighborhood always, as long as the set is not too large. Notice this cannot be true for all sets of all size. Certainly if you choose the set to be half the number of vertices, the set to be the entire set of vertices, it can't expand any further. So it's only true for small enough sets. How small? K. Every set of size at most K should expand by a factor at least A. So is the definition clear? This is, so you need to think about this definition for a while. So let's stare at it. What does it, why is it called vertex expander? It says any small set of vertices expands in this graph. That is, if you take any set of vertices, if you take one step from this set, the new set which you see will be larger than this set by some fraction. Actually, should be a little more careful. Typically, we think of A to be numbers greater than 1. Is this definition okay? Notice some of the graphs which we draw. For example, if you draw the graph which is a line graph, there's been a lot of.
No. I don't think this. Yeah.
Okay, I haven't seen. That was below my. I didn't even see. Okay.
So this NS may not contain S, right? This
NS may. So yeah. So there's sometimes people also. So sometimes I will use the notation N plus S to denote NS union S. That is the things which are reachable in one step, within one step. NS is exactly things which are adjacent to S. N plus S is things which are reachable within. This is sometimes called N1S, or also it's also called N less than or equal to 1S. There are various notions.
Actually, I was confused by the figure that you draw. It seemed like.
No. So the figure purpose. Okay. So there is this part here.
Yeah, that sliver that's outside was intention.
Yeah. It's a figure to scale. Okay. So that's the definition. Any questions on the definition? Then we should ask. The moment we give such a definition, a bunch of questions we should ask, and I'll pose those questions this time, and we'll try to answer them in the next lecture. But is the definition clear?
Yes.
Okay. So the first question, the questions I want to ask now. Okay, it's a definition. I defined an object. Do such objects exist? It could be a vacuously. There might be no such object. In particular, I want to ask, certainly complete graphs have this property. Notice that complete graphs have this property. Take any set of vertices, we look at its neighborhood, the neighborhood is everything. So it expands. Complete graphs have this property. What I want are constant degree graphs which have this property. And notice you take some graphs, which with the nice graphs which you work with, like a cycle or a line graph, these all just violate this property heavily. That is, any graph you
want
draw,
to mention what the typical value of K and A you will be looking for. Yeah.
The K will be, so K will be something like N by 100, N by 1000. It will be a linear fraction of N. It can't be more than N by 2 typically, but anything, something like N by 1000, N by 100 will be looking, K will be some N, a linear fraction of the set of vertices. A will be any number larger than 1, strictly larger than 1.
So you're looking for a constant degree graph with that is a K comma A expander for this sort of choices.
So they're interested in constant degree graphs. Constant degree graphs with K being roughly omega, K being omega n. That is, say, n over 100 or some such thing, and A being some number greater than 1, a fixed constant greater than 1. So let's make it even more clear. So A is some 1 plus epsilon. Notice A cannot be larger than D. D is the maximum you can expect. So A is certainly smaller than D. Epsilon for some constant epsilon greater than 0. That's what we want to ask this question. And let me ask the questions and then stop this one. First thing we ask, do such graphs exist? Can such graph exist? So the first thing we'll do in the next lecture is actually show if you pick a graph at random, yes, such a graph exists. That is, pick a random deregular graph, it will have this property. So the first thing we'll show. Next thing is, okay, I defined an object. Okay, such an object exists. Are they useful? They're useful. Of course, the reason I defined it was for samplers. That was the motivation behind it. It will be a while before I get back to the application to the samplers, but we'll immediately see there is a particular thing for randomness reduction that they will be useful. We will see, in fact, are they useful? This is an understatement. The sort of expander graphs have been extremely useful in the last 30, 40 years of theoretical computer science. And 3 is, okay, such random graphs exist. We'll show that they exist. Question is, can you actually construct these graphs efficiently? Can such graphs be constructed efficiently? So we'll ask all these, we'll answer all these 3 questions over the next 4 lectures. So next lecture, we will certainly see that random graphs. We'll answer the first question and we'll see an application and answer the second question to some extent. Third question will be a while before we show that we'll give a construction of the third, but over the next 4 or 5 lectures, we'll see several applications of these graphs. These are extremely useful graphs. And I have taken one viewpoint of these graphs, which is the vertex expansion. And we will see as the lecture, over the next few lectures, that these other definitions, edge expansion, random walk, spectral expansion, you can define these graphs in terms of these other concepts, and they will all lead to the same object. The same set of, if a graph is a vertex expander, it will also be an edge expander. If it's a graph is a spectral expander, it will also be this one. And these graphs also are graphs in which the random walk will mix very fast. All of these we'll show. These are some very nice graphs. They're literally magical graphs. The things they let you do are amazing. And that's what we will spend the next 4 lectures on. Any questions?
Can you say something about quasi randomness?
So quasi randomness will be this property. What we will show, this is, I'm going to eventually characterize it as something called the expander mixing lemma. I want to say that take any 2 sets S and T. If the graph were random, you expect a certain number of edges between S and T. We will show that this graph is not random. It's a fixed graph. Yet the fraction of edges between S and T will be similar to what a random graph will have. If you had picked the edges at random, it's a fixed graph, yet it will have this property. And this will be captured by something which we will call the expander mixing lemma. Yeah.
And there is another quasi randomness by Chung, Graham, and Wilson. So that is probably not something to do with this then.
No, so quasi randomness, there are multiple ways of defining, there are multiple notions of quasi randomness. So for Cayley graphs, I think if Gowers has a notion of quasi randomness in this one, where what I mean is just this property.
Okay.
Yeah. Any other questions? So all of this thing on samplers was just to lead to this object. What we want are these sampler objects. I want this sort of object here in which I can construct clouds of vertices with as few clouds as possible, yet the average on each cloud, the local average on each cloud should be close to the global average. And one attempt of doing that was to actually think of the set of points as a set of vertices of a graph and the clouds as either as walks of length t or balls of size t, and then ask which graphs will have this property. And it so happens these graphs, which allow for vertex expansion, edge expansion, random walk mix as well, will all be candidate graphs for which I could construct samplers from. So our focus is going to be on the notion, one of these notions of expansion. We'll start off with vertex expansion. Very soon in next lecture, we'll move to spectral expansion. We'll see it's an equivalent notion and we'll work with the expansion. That's going to be the focus for the next 4 or 5 lectures. Any other questions? Okay, then we can stop.